So in this video we're going to develop a formula for the surface area of a surface of revolution. And all a surface of revolution is if we take a curve in the xy plane, it's described by some function of x, and we either rotate that curve around the x-axis or we rotate that curve around the y-axis. And when we rotate the curve around in this example, the x-axis, we wind up with a surface that's carved out by this line or curve as it's rotated through space. And what we want to do is develop a formula that will let us get the surface area of the shape that's been swept out as we rotate the curve. The approach that we take is similar to the approach that we did in video 1 for finding the arc length of a curve. The idea is if we want to know the surface area that we get when we take a curve like this and rotate it, for this example, let's go around the x-axis. What we want to do, if we're rotating that curve over an interval from A to B, is we want to take and cut the interval from A to B up into chunks. So in this example, I've cut the interval from 0 to 2 into 4 distinct chunks. And each boundary where I've made a cut corresponds to a point on the curve. And in this case I did 4 chunks, but you don't have to do 4 chunks, you do n chunks. I'm going to cut the interval from A to B into n chunks. And n can be any number that we want, and we can let n go to infinity. And the idea is the size of a chunk is going to be given by, if you're working over an interval from A to B, the length of the interval you're working over, the length of the interval is going to be b minus a. b minus a gives you the length from the start to the finish. And then if you decide to cut b minus a, the interval from a to b into n chunks, this delta x right here, this change in x between any 2 chunks you've cut the interval into, is just going to be the length of the interval divided by n, where n is the number of pieces you cut the interval into. So we get this delta x equals b minus a over n. And what we want to do is then recognize that this cuts our interval up into boundaries, and between any 2 points on the line corresponding to how we cut the interval, we can draw in the line segment. And then what we can do is estimate the surface area of revolution, not by revolving the line around the x-axis, but by revolving the line segment around the x-axis. And when we revolve this line segment around the x-axis, we get a shape that's called a frustum. And we actually know how to calculate the surface area of a frustum. So a frustum surface area is 2 pi times r1 plus r2 divided by 2, where r1 is just this radius and r2 is the radius at the other end of the frustum. So this is an average radius. So we're really looking at, hey, there's an average radius, r1 plus r2 over 2. And when we think about it, the circumference of a circle is 2 times pi times radius. So this is 2 times pi times the average radius. This really, in a solid sense, is the average circumference over this slant length right here. So what we can do then is cut the region up into lots of pieces, n pieces in fact. And then for the ith piece, let's say this is the ith line segment that we make. We're going to take that ith line segment, which has 2 radii, extending down to the x-axis. This is the ith radii, and this is the I minus first radii, corresponding to our r1 and r2 here. We rotate this line segment, we get a frustum with radii r sub I minus 1 and r sub I. And then I could calculate the surface area of the frustum I get when I rotate this line segment. So here's what you would get. You would get, for just the ith line segment, what you would get is you would get the 2 pi, and it would be times the r sub I plus r sub I minus 1. It would be the sum of the two radii divided by 2. That would be your average radius, which is going to be sitting right here in the middle. And then we would need to multiply it by the slant length here, by the slant length, which is just the length of this line segment. But in video 1, when we found the formula for arc length, we actually calculated the length of this line segment. What we discovered in that video is that this is the square root. I'm going to get rid of that picture to give myself a little extra room here. Oh, and then I didn't get rid of it. Get rid of you and bring this back up. So what we discovered was the length of this line segment was 1 plus delta y sub I, because we had in video 1 we had the width was delta x and the height was delta y sub I. The delta x's were the same everywhere, so we didn't need to subscript them. So it was delta y sub I squared over delta x squared is what we got. And this was times delta x on the outside. And this would be the surface area of just one of these frustums. So if I wanted to estimate the surface area I get by rotating the entire curve around the x-axis, I would add up the frustums created by each of the n line segments. So I'd just add them all up. It would take the sum. We would take the sum from I equals 1 to n of each of the I line segments rotated around the x-axis. And what we could do then to make the estimate exact would be to let n go to infinity, because if we let n go to infinity, as n goes to infinity, the delta x's get smaller and smaller and smaller. B minus a over n as n goes to infinity becomes 0. So delta x winds up approaching 0. And what that's going to do is a couple things. It's going to pull the r sub i's closer and closer to the r sub I minus 1's. So these radii will get closer and closer together. And in fact, the limit as delta x goes to 0 of r sub I plus r sub I minus 1 over 2 is actually going to be equal to just 2r sub I over 2, because r sub I will equal r sub I minus 1. The two radii will become the same length as the delta x's get smaller and smaller and smaller. So the formula actually, if we take the limit as n becomes infinitely large of the sum from I equal 1 to n, things start to simplify. The 2 pi, because it's a constant, can factor out of the summation. The r sub I plus r sub I minus 1 simplifies to just the radius. And because we're working with respect to the x-axis, we would want to know the radius as a function of x, because we got a delta x here. And we actually get, in the limit, delta y sub I actually becomes dy, and delta x is dx in the limit. So we wind up with dy dx squared, and delta x is really dx in the limit. But dy dx is just the derivative. So we wind up just getting the interval from a to b, sum everything up from the beginning to the end with the 2 pi on the outside. We need the radius as a function of x from here. And this is just the arc length formula from video 1. This is just, hey, take the derivative of x and square it times dx. And then this is going to give you the exact area of the surface of revolution. So this slide here summarizes that formula. Again, this formula is for an x-axis rotation, and what we could do is ask ourselves, how would the formula change if we were instead doing a y-axis rotation? Well, then the surface area, because you were doing a y-axis rotation, if we're running over the interval from a to b on the y-axis, we would still need to know the radius, because we're going to be rotating these line segments with the radii. but the radii are going to be with respect to the y-axis now. We're rotating this way around the y-axis. So we would need to know the radius as a function of y instead of as a function of x. And we would calculate the arc length. We would need a function of y, not a function of x. And instead of dx, this would be dy if we did a rotation with respect to the y-axis.